Welcome everybody to the next session on battery modeling. So I'm Srijit here from Nairo Research. So in this technical video, we are going to discuss that how we can create an amorphous system using simulated annealing in the Amsterdam Modelling Suite using reactive force field. So earlier we have completed the optimization steps related to this battery modeling. So in this step, as I said earlier, that using AMS, the creating amorphous systems is a well-established workflow, especially for glasses, polymers, amorphous oxides, solid electrolytes, and battery materials. So the conceptual idea, speaking about this amorphous structures, it lack long-range order, so they are not built directly from crystallographic data. So instead of that, one starts from a random or poorly ordered atomic configuration and uses high temperature molecular dynamics to melt the system, followed by controlled cooling or annealing to crunch it into an amorphous state. So in AMS, this is achieved using simulated annealing via MD rather than direct geometry optimization. So in this case, in AMS, this workflow is supported using either DFTB, React-Surface or classical force fields. And for small systems, even DFT-based MD. So we have already prepared the structure earlier. So using AMS Builder, we have created our material. But in this specific example, I have already done the optimization in the previous step. The previous session. So here, I'm just going to give you an idea that what are the different steps we have performed. It's already I have performed the calculation, but I'm going to show you that what are the different inputs. So I have selected the reactive force field engine. I have selected the task molecular dynamics and the force field which we have selected earlier, lithium sulfide force field from the force field library. And I'm going to set the number of steps 30,000. So why this 30,000 steps is that the initial relaxation after we conducted the initial relaxation, we need to run a soft geometry optimization to remove the bad contacts for the MD, which we have already done. And to set up the high temperature melt, we need to perform NVT. So the temperature is around in the range of 300 to 1600. And then why we have setting the temperature is that we need to gradually reduce the temperature from high temperature to 300 Kelvin. So in order to set the cooling range after the fast quenching gives a more disorder, and then the slow quenching gives a more relaxed amorphous structure. For example, if you are setting at 200 Kelvin to 300 Kelvin over 500 to 100 picoseconds, it is done using the schedule, or multiple MD simulations will decrease. The runs will decrease the temperature. So that's what the purpose of setting at this temperature range from 300 to 1600 and back to 300, and the duration from 5000 the maximum to 20,000 to 5000 again. So once we set the damping constant to 100 times per second, and then we will execute the calculation. So I have already performed the calculations in order to save the time, because I have taken the respective example from the case study which we were discussing earlier. So here I have followed the same steps from start until 500. The step, then from step 5000 to 25,000 to heating up from 300 Kelvin to 1600 Kelvin, and from step 25,000 to 30,000 cooling down from 1600 Kelvin to 300 Kelvin. So the same methodology I have employed for setting up the simulation to build an amorphous system. So let me show you that how the output of this calculation, because I have already performed the calculation earlier. You can see that 30,000 steps are finished, and let me show you that from AMS movie we can see the animation of that typical example. Let me maximize the screen, and you can see this is the expected outcome of that simulated annealing methodology. where you can see that the graphical representation of this process. So this is actually the representation of how to create or how to generate an amorphous system. So this is an important step while we proceed to diffusion coefficient calculation in battery materials. So in the next step, I will brief you that how we can validate the results and how we can calculate the diffusion coefficient in battery material model. Thank you.